May 1940, Detroit, Michigan, the Packard Motor Car Company assembly line. Chief Engineer Jesse Vincent stands in the engine testing facility, watching smoke pour from the crankcase breather of a brand new V1650 Merlin engine. This isn't just any engine, it's the American-built version of the Rolls-Royce Merlin, the legendary power plant that will drive the P-51 Mustang, arguably the best fighter of World War II. The engine has been running for 12 hours. It should run for hundreds, but the oil consumption is catastrophic, nearly a gallon per hour. Compression is dropping. Power output is falling. Vincent knows exactly what's happening. The piston rings are failing. He walks to the disassembly bay where another test engine sits with its cylinder head removed. A technician shows him the problem. The piston rings, thin bands of metal that seal the piston against the cylinder wall, are already showing visible wear. Deep grooves score their faces. In some cylinders, the rings have lost tension entirely, allowing combustion gases to blow past into the crankcase. "How many hours on this one?" Vincent asks. 47, the technician replies. Vincent does the math in his head. The British Merlin, built by Rolls-Royce in England, routinely runs 300 to 400 hours between overhauls. This American-built version is failing after 50 hours. At this rate, every engine they produce will be worthless. The problem isn't the engine design. Rolls-Royce's engineering is impeccable. The problem isn't the manufacturing. Packard's machinists are among the best in America. The problem are the piston rings themselves. And the reason is both simple and terrifying. America doesn't have the metallurgy to make them properly. In 1940, as war clouds gathered and America began the largest military production program in history, the United States faced an uncomfortable truth. For all its industrial might, for all its manufacturing capacity, American industry couldn't produce one of the most basic components in every internal combustion engine: a piston ring that would last. British engines used rings made with metallurgy the Americans couldn't replicate. German engines used technology the Americans didn't have. And American engines, the engines that would need to power thousands of aircraft, tens of thousands of tanks and trucks, were failing because nobody in the United States knew how to make a ring that wouldn't wear out in days. This is the story of how one company in Michigan solved the crisis that threatened to cripple American war production, how engineers turned to an unconventional solution that British and German metallurgists had dismissed, and how chrome plating, a decorative process used on car bumpers, became a critical military technology that American industry could scale up when traditional methods failed. Let me explain what a piston ring does, because understanding the function makes the crisis more clear. A piston is a cylindrical slug of metal, usually aluminum alloy, that slides up and down inside an engine cylinder. The piston is slightly smaller in diameter than the cylinder, with a gap of typically 0.003 to 0.006 inches all the way around. This gap is necessary for clearance, lubrication, and thermal expansion. But that gap is also a problem. When the air-fuel mixture ignites in the combustion chamber, it creates pressure, potentially 1,000 plus psi in a high-performance engine. If that pressure escapes past the piston into the crankcase below, you lose power. Worse, combustion gases contaminate the oil and create blow-by pressure that can damage seals and gaskets. Piston rings seal that gap. They're thin bands of metal, typically 3 per piston, that sit in grooves cut into the piston's outer surface. The rings are slightly larger in diameter than the cylinder, so when installed, they compress and create outward spring pressure against the cylinder wall. This outward pressure, combined with combustion pressure forcing the rings down into their grooves, creates a gas-tight seal. The rings also serve a second function. They scrape oil from the cylinder wall, preventing it from entering the combustion chamber and burning. For this to work, the rings must maintain spring tension over hundreds of hours, survive temperatures exceeding 500 degrees Fahrenheit, resist wear as they slide against a cylinder wall millions of times, seal against pressures that would blow them out of their grooves if they weakened. In 1940, making rings that met all these requirements was sophisticated metallurgy. The rings needed to be made from cast iron, specifically a high-carbon cast iron with carefully controlled alloy content. Too little carbon and the iron wouldn't have sufficient hardness. Too much and it became brittle. The iron needed graphite nodules dispersed in specific ways to provide lubricity without sacrificing strength. The rings also needed precise heat treatment. After casting, they were machined to exact dimensions, then heat treated to relieve stresses and set their final hardness and spring characteristics. This heat treatment was as much art as science. Time, temperature, and cooling rate all had to be precisely controlled. Finally, the rings needed a wear-resistant surface. In service, the ring face slides against the cylinder wall under pressure and at speed, with only a thin film of oil separating metal from metal. This creates wear, unavoidable, but manageable if the materials are right. British manufacturers in 1940 had perfected this process over decades. Companies like Welworthy and Hepworth and Grandage produced rings that could run hundreds of hours in high-output aircraft engines like the Merlin. Their metallurgical expertise, their foundry techniques, their heat treatment processes, all refined through years of experience, produced rings that simply worked. American manufacturers in 1940 didn't have that expertise. America had a piston ring industry. Several companies made rings for automotive engines, but automotive rings and aircraft rings were different animals. A car engine in 1940 might produce 100 horsepower from 300 cubic inches of displacement. It ran at modest RPM, maybe 3,500 to 4,000 maximum. It operated at relatively low specific output, horsepower per cubic inch. Piston rings for these engines didn't face extreme conditions. Aircraft engines were entirely different. The Merlin produced 1,400 plus horsepower from 1,650 cubic inches. It ran at 3,000 RPM continuously, with short bursts to 3,600 RPM. Specific output was nearly triple that of automotive engines. Everything ran hotter, harder, faster. American piston ring manufacturers had never built rings for these conditions because American aircraft engines of the 1930s were relatively low-output radial designs that didn't push the limits the same way. When Packard received a license to build a Merlin in 1940, they initially tried to source rings from American suppliers. The results were disastrous. Rings from automotive suppliers failed within hours in Merlin test engines. The metallurgy wasn't right, the iron was too soft or too brittle, or didn't have the correct carbon structure. Heat treatment was inconsistent. Quality control was inadequate for aircraft standards. Packard tried importing rings from Rolls-Royce in England. This worked, but it was clearly unsustainable. Britain was at war, under aerial bombardment, with their own massive production requirements. They couldn't supply rings for both British and American engine production, and shipping rings across a U-boat-infested Atlantic made no strategic sense. The U.S. War Department convened meetings with American metallurgists and ring manufacturers. The message was stark: solve this problem or American aircraft production will fail before it starts. Multiple companies attempted solutions. Some tried to replicate British metallurgy by analyzing imported rings and reverse engineering their composition and treatment. This had limited success. Even knowing what the British were doing didn't mean American foundries could duplicate it. The problem was systemic. British foundries had specific casting techniques, specific furnace designs, specific institutional knowledge built over decades. American foundries were set up differently, optimized for different products with different expertise. One company took a different approach entirely. The Hastings Manufacturing Company in Hastings, Michigan, was not the largest piston ring manufacturer in America. Founded in 1915, they'd built a solid reputation in automotive rings, but were not a major military supplier. In 1940, Hastings was run by Floyd Hastings, grandson of the founder. Floyd was an engineer who'd grown up in the business and understood both the technical and practical sides of ring manufacturing. When the military crisis became clear, Hastings attended the War Department meetings. He listened to other manufacturers talk about trying to match British metallurgy, and he had a realization. They were approaching the problem wrong. The British solution, specific cast iron alloys with specific treatments, worked brilliantly, but it required expertise and infrastructure America didn't have and couldn't develop quickly enough. Trying to match it meant playing catch-up in a game where Britain had a 30-year head start. What if, Hastings thought, you didn't try to match British metallurgy? What if you solved the wear problem differently? The fundamental issue was wear resistance. Rings wore because their surface, iron sliding against iron or steel, abraded over millions of cycles. British metallurgy minimized this wear through carefully optimized iron alloys and heat treatment. But there was another way to create a wear-resistant surface: coating. Chrome plating had been used industrially since the 1920s. It was primarily decorative: car bumpers, bathroom fixtures, anything that needed a bright, corrosion-resistant finish. But chrome had properties beyond appearance. It was extremely hard, harder than any practical steel. It was smooth, reducing friction, and it bonded well to steel substrates. What if you made a piston ring from conventional American cast iron? Nothing fancy, just good quality material American foundries could produce reliably, and then chrome-plated the face. The chrome layer would provide wear resistance. The iron substrate would provide strength and spring properties. You'd be combining two well-understood American technologies, iron casting and chrome plating, instead of trying to master one complex British technology. It was unconventional enough that most metallurgists hadn't considered it seriously. Chrome plating was for decoration, not for critical mechanical components. But Hastings thought it might work. Hastings began experiments in late 1940. The challenges were immediate and substantial. Challenge 1. Plating thickness. Decorative chrome plating was typically 0.0003 to 0.0005 inches thick, a few 10,000ths of an inch. This was enough for appearance, but far too thin for a wear surface. Hastings needed plating thick enough to survive the wear of hundreds of hours of operation. Through testing, they found that approximately 0.004 to 0.0006 inches of chrome provided adequate wear resistance, roughly 10 times thicker than decorative plating. This required longer plating time and careful process control to ensure uniform thickness. Challenge 2. Adhesion. Chrome had to bond strongly to the iron substrate. In decorative work, if plating peeled, it was cosmetic. In an engine, peeled chrome would destroy the cylinder in seconds. Hastings engineers developed surface preparation techniques, careful cleaning, specific etching processes that promoted strong adhesion. They also experimented with undercoats, thin layers of other metals like nickel, that improved chrome bonding. Challenge 3. Porosity. Thick chrome plating tended to develop microscopic cracks and pores during the plating process. In decorative applications, this didn't matter. In an engine, these pores could retain oil, actually beneficial for lubrication, or potentially lead to accelerated wear if they propagated. Hastings found that controlled porosity was actually advantageous. Microscopic pores in the chrome surface retained oil, improving lubrication. This became a feature, not a bug. Later, they would deliberately create controlled porosity through specific plating techniques. Challenge 4. Ring geometry. Piston rings aren't simple bands. They have complex cross-sections with bevels, radii, and precise dimensional tolerances. Plating added thickness, which meant rings had to be machined undersized to account for the plating thickness, then plated to final dimension. This required careful coordination between machining and plating operations, with tight process control to ensure final dimensions were within tolerance, typically plus or minus 0.001 inches. Challenge 5. Heat treatment. Chrome plating required the workpiece to be in an electroplating bath, aqueous solution of chromic acid at specific temperature, but rings also needed heat treatment for proper spring characteristics. Hastings had to sequence operations carefully, machine the ring, heat treat it to set spring properties, then plate it. The plating process temperature, around 130 to 150 degrees Fahrenheit, was low enough to not affect the prior heat treatment. By early 1941, Hastings had working prototypes. Initial testing in automotive engines showed promising results. Chrome-faced rings showed significantly less wear than conventional rings. The real test would be aircraft engines. Packard agreed to test Hastings' chrome-plated rings in Merlin engines in spring 1941. The first tests were cautious, single engines, short runs with careful monitoring and frequent inspections. The results surprised everyone. Chrome-plated rings not only matched British rings, they exceeded them in some measures. Wear rates were lower. Oil consumption was reduced. The rings maintained tension and sealing over longer periods. After 100 hours, Packard engineers tore down test engines and examined the cylinders. Wear was minimal, barely measurable. The chrome surfaces showed polishing but no significant material loss. After 200 hours, results were similar. After 300 hours, approaching the overhaul interval for combat engines, the chrome rings still showed excellent condition. More testing followed, now including engines run under combat simulation, full throttle operation, rapid throttle changes, high-altitude conditions, tested in pressure chambers. The chrome rings held up. By late 1941, Packard was convinced. They approached other engine manufacturers, Allison, which built the V1710 engine for P-38s and P-40s, Wright Aeronautical, radial engines for Navy aircraft, Pratt & Whitney, more radials, and shared test results. Other manufacturers ran their own tests. Results were consistent. Chrome-plated rings worked, and they worked well. The Army Air Forces and Navy Bureau of Aeronautics reviewed the data and made chrome-plated rings a standard specification for military aircraft engines. By 1942, it was mandatory. Making a few hundred rings for testing was one thing. Making millions for war production was entirely different. Hastings had to scale up massively. In 1940, they employed perhaps 200 workers and produced rings primarily for automotive aftermarket. By 1943, they would need to employ thousands and produce rings for tens of thousands of military engines. The chrome plating process was labor-intensive and required careful control. 1. Machining. Rings machined from cast iron blanks to undersized dimensions. 2. Heat treatment. Rings heat-treated to set spring properties and hardness. 3. Cleaning. Extensive cleaning to remove all oils, oxides, and contaminants. 4. Plating. Rings suspended in electroplating tanks filled with chromic acid solution, with electric current passed through for several hours depending on desired thickness. 5. Post-treatment. Rinsing, drying, and final inspection. 6. Final machining. Light finishing operations to ensure final dimensions. Each step required quality control. A defect at any stage meant scrapped parts. Hastings built new facilities in Hastings, Michigan, and established additional production at other sites. They trained hundreds of workers, many of them women, as men were drafted, in the precise techniques required for military specification plating. The U.S. government, recognizing the strategic importance, provided funding for facility expansion and prioritized allocation of materials. Chrome metal itself was a strategic material, needed for armor steel and other applications, but chrome ring production received adequate allocation. Other manufacturers also began producing chrome-plated rings under license from Hastings. Perfect Circle, another major ring manufacturer, set up chrome plating facilities. So did Thompson Aircraft Products and several others. By mid-1942, American industry was producing chrome-plated piston rings in quantities sufficient for all military engine production. Let me give you scale because the numbers are staggering. Between 1940 and 1945, the United States produced approximately 324,000 aircraft engines, all types. Millions of automotive engines for military trucks and vehicles, hundreds of thousands of marine engines. Each aircraft engine typically had 12 to 24 cylinders, depending on type, inline versus radial, size. Each cylinder had 3 to 4 piston rings. A conservative estimate, the U.S. military needed over 25 million piston rings for aircraft engines alone during World War II. Add automotive and marine applications, and the total easily exceeded 50 million rings. All of them, every single one for aircraft engines, most for high-performance vehicle engines, were chrome-plated. Hastings alone produced millions. Other manufacturers produced millions more. The chrome plating infrastructure built for this purpose represented one of the largest precision electroplating operations in history. And it worked. American aircraft engines gained a reputation for reliability that partly stemmed from superior piston ring design. Engine overhaul intervals for American engines often exceeded British or German equivalents. The British, when they learned about American chrome-plated rings, were initially skeptical. British metallurgists had considered and dismissed chrome plating as unsuitable for critical engine components. But American test data was convincing. By 1942, British manufacturers began experimenting with chrome-plated rings. Some British engines later in the war used them, though British manufacturers never switched entirely from their traditional metallurgy. The British approach wasn't wrong, their rings worked excellently, but the American approach was easier to scale up quickly with the infrastructure America had available. The Germans faced a different situation. German piston ring technology was excellent, comparable to British. German engines like the DB 601 and 605 used in Bf 109 fighters, and the Jumo 211 and 213 used in various aircraft had high-performance rings made using advanced metallurgy. But Germany, perpetually short of strategic materials, couldn't afford to divert chrome metal to piston ring plating. Chrome was needed for armor steel, for gun barrels, for critical military applications. Using it for piston rings, when adequate rings could be made without it, was an unaffordable luxury. A captured German technical document from 1943 mentions American chrome-plated rings, noting, "American practice of chrome plating piston rings shows reduced wear characteristics. However, implementation would require allocation of chrome resources not currently available for this application." In other words, nice idea, we can't afford it. This is a recurring theme in World War II technology. Often, all sides understood advanced techniques. Whether they could implement them depended on resources, infrastructure, and strategic priorities. After World War II, chrome-plated piston rings became standard throughout the automotive and aircraft industries worldwide. Modern car engines, the one in your driveway, almost certainly has chrome-plated top compression rings. The technology developed frantically in 1940-42 to solve a military crisis became universal civilian technology. Later developments refined the concept. Plasma coating and other advanced surface treatments supplemented or replaced some chrome plating applications. Molybdenum-filled chrome plating, where molybdenum particles are embedded in the chrome layer, improved wear resistance further. Controlled porosity techniques deliberately created microscopic surface texture that retained oil. But the basic principle, hard coating on an iron substrate, remained the standard approach. Hastings Manufacturing Company continued as a major piston ring manufacturer throughout the 20th century. They eventually merged with other companies, but their name remained associated with quality rings for decades. The engineers who developed chrome-plated rings in 1940-42 solved a critical problem under intense pressure. Their solution wasn't the most elegant from a pure metallurgy standpoint. British cast iron alloys were arguably more sophisticated, but it was the solution American industry could implement at scale with available resources and expertise. The piston ring crisis of 1940-41 illustrates something important about industrial mobilization. You can't always use the best solution. You have to use the solution that works with the capabilities you have. British piston rings represented decades of accumulated metallurgical expertise. Trying to duplicate that expertise in months was impossible. American engineers like Floyd Hastings recognized this and found an alternative path. Chrome plating wasn't obviously better than British metallurgy, it was different. It leveraged American strengths, electroplating technology, chrome metal supply, mass production capability, while avoiding American weaknesses, limited experience with specialized cast iron alloys. This pattern repeated throughout American World War II production. American radial aircraft engines weren't necessarily superior to inline designs, but American manufacturers knew how to build them at scale. American ship construction used welding extensively because American shipyards were set up for welding, even though riveting was sometimes technically superior. American tank design emphasized reliability and producibility over individual technical superiority. The piston ring story is one small example of a broader truth. Industrial warfare is won by the side that can produce adequate equipment in overwhelming quantity, not by the side with the most sophisticated individual technologies. Chrome-plated piston rings weren't a miracle technology. They were a pragmatic solution to a critical problem, implemented with ruthless efficiency by American engineers and manufacturers who understood that working technology today beats perfect technology next year. If you've ever changed a piston ring on a car, a motorcycle, a lawnmower, you've held technology that emerged from a World War II crisis. That chrome-plated surface? That's the same technology Hastings Manufacturing developed in 1941 when America faced the humiliating reality that it couldn't make a basic engine component properly. Next time you see an aircraft engine, a vintage warbird at an airshow, a modern turbine with piston-driven accessory units, remember that its ancestors were nearly grounded by something as simple as piston rings. And remember that the solution came not from trying to copy what Britain did better, but from American engineers asking, what can we do with what we have? America had no adequate piston rings in 1940, so Hastings made chrome-plated rings instead. And they worked so well they became the standard worldwide. That's not just a story about metallurgy or manufacturing. It's a story about engineering pragmatism, about finding solutions that fit your capabilities, about doing what works instead of what's theoretically optimal. Jesse Vincent, standing in that Packard engine test facility in 1940, watching American-built Merlin engines fail because American rings couldn't survive, faced a crisis that threatened the entire aircraft production program. Chrome plating solved it. A decorative process used on bumpers and bathroom fixtures became a critical military technology because American engineers were willing to think unconventionally. And that's knowledge you now have.